This is the last section in Unit 4. This is Section 4.6. I can use linear functions in context. So we're going to be applying the math that we've learned about linear functions in story problems in real-world situations. So the warm-up here says when referring to banking, it says, what is a balance? Well, if you've heard the word balance before, you might know that it is the money, and I'm just going to use a dollar sign here. It's the money in an account. Okay, it's the money in an account. Now, that balance could be a loan balance. It would be the money you owe, or it can be the money that you put in a savings account. And then the next one says, what is a withdrawal? When you draw money, you take it out. So it's the money you take out. And then the next question says, what is the opposite of withdrawal? Well, the opposite of withdrawal would be that's the money that you put in, but there's a word for that. When we put money in an account, we call that a deposit. We'll call that a deposit there. Now, linear functions are really useful in the real world, and they're actually one of the easiest mathematical models to use. And a model can help us make predictions. It can help us make decisions. And we want to be really good at linear models because if you know how linear models apply in the real world, we'll be better able to deal with more complex models that you're going to see down the road that aren't quite as easy as this. So let's take a look at example 1. We've just got 2 examples to look at here. On example 1, it says the North American and Eurasian continental plates are drifting apart at an imperceptible rate of 2.5 centimeters per year. At a fissure in Iceland, the plates are currently 1.5 meters apart. And like all the other questions that we've been dealing with lately, if you need to skip around so that you can answer these, that's totally okay. It's not like A has to be done first. There are times where you might want to do some before that, but not every single time. So it says write a linear function d of t where t represents the time in years. So notice what they've done for us. They've declared the variables here, and d represents the distance between the plates, and it says watch the units. So this is a classic math problem right here where you'll notice this one says 1.5 meters apart. So right now they're 1.5 meters apart, but every year they're spreading apart by 2.5 centimeters. So we've either got to change this into meters or we've got to change this into centimeters. And it's going to be a lot easier if we change this into meters. So if you recall, there are actually 100 centimeters in a meter. So this 1.5 meters is actually 150 centimeters. So we're going to use this value right here because it matches up unit-wise with this value right here. So just make sure if you ever see something like that, that's something we've got to be aware of. So here's what we're going to write down. We're going to write d of t, and it says this is a linear function. So we know that we're looking for a slope value right here, and then we're going to multiply it by the independent variable, and then we're going to add whatever the initial value is, whatever the y-intercept is. In this case, it would be a d-intercept. So the d stands for distance, so one of the easiest things to do would be to say, well, this value right here, that is the y-intercept, okay? That's the distance intercept. That's the distance that they are apart when we kind of click the stopwatch and so forth. So that's going to be 150. Now, if you caught on to that, that's totally okay. If you didn't, there's only 2 numbers in the problem, and they've got to go somewhere. They've either got to go here or here. If you figured out 150's got to go here, that means the 2.5's got to go here. And here's another reason why that 2.5 has to go there. This is 2.5 centimeters per year. So if I write 2.5 centimeters per year, you'll notice that what we have here is we've got centimeters on the top, we've got a distance on the top, and then we've got a time on the bottom. So this is a distance and this is a time, just like we've got, remember, our independent variable on the bottom, like x, and our dependent variable on the top. So this is like having the y's over the x's. So just kind of keep that in mind, but this is the right one. It says, what's the y-intercept? The y-intercept is 150, and what that means is 0, 150. So at time 0, at time equals 0, it's 150 centimeters apart, that 1.5 meters that we talked about earlier. It says, what's the rate of change? So here's where we're talking about this one right here, 2.5 centimeters per year, and I'll put a 1 right there. And then it says, consider how you will scale and label the axes and then graph the function. So let's go ahead and take this and let's try and graph this. So what most people would do is they'd say, okay, let's see, I've got to get up to 150 right here. So let's count by tens. So again, I'm just going to mark every other one here. So this is going to be 20 and 40 and 60 and 80 and 100 and 120 and 140 and 160 and this would be 180 right here. So 180. And we start off at 150, so it's going to be right here. And then we go up 2.5 centimeters per year. Oh, I forgot to do this. Let's scale this. We're not going to scale that the same because we're just going to do 2 and 4 because this is keeping track of things in years. So there's a 10 and 12 and 14 and so forth. And I'm going to put time right here in years. And then this one right here, remember this was a distance. And this is in centimeters, so we'll put the measurement right there. And then we're going to go, let's see, this is positive, so this is going to go up 2.5 centimeters. So if this is 150, and I'll go ahead and put that, we're going to go up 2, so that's going to be 152.5. So that's going to be maybe about right there, and we're going to do that in 1 year. And then another 2.5, so 2.5 plus 2, that's a 5, so 155 in 1 year. Another 2.5 would be 157 in a year. And then finally, after 4 years, we go 10 centimeters, okay? So we could graph it like this, but you'll notice this doesn't look very good. And this is where this little asterisk comes in. It's really hard to graph. We've got to graph 3 points in between before we get to another convenient point. So I'm going to go ahead and erase this, and I'm going to come back and I'm going to show you something else. Okay, I've gone ahead and erased the scaling on the vertical axis here, the distance axis, and I've left the horizontal axis, the time axis on here, because this really wasn't the problem. The problem was things were so scrunched up here between the 150 and the 160 and so forth. It was really hard to see what was going on. So here's what we're going to do. A broken axis is when you've got a bunch of things kind of scrunched together at the top, and we want to get rid of the bottom where a bunch of stuff doesn't happen. So what we do is we draw a little crooked line through here, break that axis, and then here's what we'll do. We're going to start off at 150, and then we'll do 152, and 154, and 156, and 158, and then 160. And then if we want to keep going, we could go 162. So what we're doing here is we're counting by 1 on each one of these. I suppose if we wanted to put 148 there, that would be fine. So 50, 52, 54, 56, 58, and then 60. Now, we put our starting point on here. This is going to be 150, and now we have to go up 2.5 centimeters. Well, remember, this is still scaled in centimeters, so what we're going to do is we're just going to go up 2.5 centimeters, so that's going to be about right here. So 1, 2.5 in 1 year, and then a half, 1 and 2, so we're going to be right here, and then in 1 year. Now, you'll notice that in 2 years, we've gone from 150 up to 155, and then we went over 2 years. So we're going to go up 2.5 over 1 year, 2.5 centimeters over 1 year. And you'll notice with that same 4-year path here, 4 years went by and we went 10 centimeters up. So this looks a little bit better. Now, it does say, is this discrete or continuous? I think I want to answer this one right now. This is going to be continuous because it doesn't just suddenly jump apart. That would be called an earthquake. So it doesn't suddenly go another 2.5 centimeters apart. It does a little bit and a little bit and a little bit and a little bit and a little bit, and then in a year, it's 2.5 centimeters and a little bit and a little bit. So this covers all of those in between. So this is going to take a look like this. We'll put an arrow on there, and it says find the domain. The domain, according to the way we've done this, is we're going to start off at 0, and we'd assume that this is just going to continue forever. That rift is going to continue going like that. And then the range is going to be from 150 all the way to, well, again, it's just going to continue spreading apart, so that's going to be infinity. And then clearly this is increasing, and the reason why this is increasing is because that slope is positive. That's going to make it go up like that. Okay, let's take a look at the next problem. Okay, on this problem it says Katie had a summer job and would make deposits in a savings account to use as food and fun money at college. By the end of the summer, her balance was $2,800. She knows she will withdraw $250 on the first of each month for the 10 months she's away at college. Again, any order you want is fine here, but let's see if we can go through and answer these. It says define variables and use them to write a linear function that represents this situation. Well, what's going on here is she's got this money in her account. We really don't care what happened in the deposits in the summer. What we care is that account when she left off for school is $2,800, and then on the first of every month, she's going to take out $250. So her balance, the money in her account, is going to go down every single month. And when we're talking about measuring things in months, that's going to be a time, and the more time goes by, the lower that balance is. So here's what I'm going to do. Let's use B for balance. B for balance, and I'm going to put a $sign on that right there. And then let's use T for time. T is going to be time, and I'm going to put MOS here. So that's time in months. And then it says, what's the y-intercept? Okay, we've actually got to write that function there. So if we're going to write down a function with the balance as a function of time, we're going to write B of T. So the balance is a function of time, and she's withdrawing $250. So minus $250 every single month. So again, there's our rate, there's our slope right there, and there's our independent variable T, and then we write plus 2,800. So that 2,800, because that's the starting amount, okay, so that's like the 0, 2,800. That's how much she starts with. That's the y-intercept. And then this right here, that's the $250 every single month. So the y-intercept is 2,800. And what that means is 0, 2,800. And we'll write this. Balance was 2,800 to start. Okay? And the rate of change is going to be that, let's see, what have we got here? Negative 250. So that's negative 250. I'll make a little bit of room for this so we can make sense here. Negative $250 per month. Okay? All right. And discrete or continuous? Well, let's think about this. It's going to start out with $2,800, and then she's going to go in and pull $250 out. So it's going to go down to $2,550. And then she's going to leave that in there, and it's going to drop down again. So this is going to be discrete. Okay, because it's going to be every single month she's going to go in there and pull some out. Is it increasing or decreasing? It's decreasing. And the domain and the range. Gosh, let's think about this. We were kind of just talking about this. The domain. So the domain is the time. Okay, that's the independent variable here. So we'd start the clock at 0 months, and then it would be 1 month and 2 months and 3 months and 4 months and 5 months, all the way to, and it doesn't continue on forever. It says she's going to be there for 10 months. So 10 months right there. So that's going to be the domain. And then the range, let's think about this one. The range, it would start off at, and this one I think I'm going to give you permission to write it backwards. The range would start off at 2,800, and then it's going to drop down 250. So that's going to be, let's see, what did we say it was, 2,550? And then it's going to be 250 less than that, so that's going to be 2,300. And then it's going to be 2050, and it's just going to kind of continue going on like that. Okay, and so we could actually put, I guess on this one we could put set brackets on this. That actually might be a better way to go. Then we're kind of not locked into like interval notation or something like that. So I think I'm going to go ahead and do that. So we'll go ahead and do this. We'll do it's the set of numbers from 0 to 10. Those representing month 0 to month 10. And then it's the dollar amounts from 2,800, then 2,550, then 2,300, and so forth. And then it says, what would this function look like if we graphed this? Well, this is kind of an interesting question. So I'm going to go ahead and put a little axis right here. So this is going to be months, and this is going to be the dollars in the bank accounts. So we're going to start out at 2,800, and then it's going to stay there. And then the first month that she's at school, she drops down to 2,550. So it drops down to this, and then it drops down again, and it drops down again. So it's going to maybe look something like that, but you could stop and think about this. This is actually a little bit more interesting than just a bunch of dots. For that first month, it just stays there. And then all of a sudden, it drops down like this. And then all of a sudden, it drops down like this. Whoops, I need an open endpoint right there. So we'll do open endpoint. So that's what it looks like. Okay, so it continues going down for the 10 months that she's at school. Now, we're not going to see many like this, but it is kind of an interesting one to think about. So go ahead and circle the self-assessment right there. Take a look at these problems. Good luck on the assignment.